All right. So I lied with the last video being strictly what you need to know for pre-circuit fundamentals. There's actually this part and another video that I need to do to talk about some more stuff. So with the second part, right, now that we know, and let me write this. So this is pre-circuit. I got the wrong colors here. We have pre-circuit fundamentals part 2. Just say 2. Okay. So for the last video, we discussed Ohm's law. So let's just write that down really quick. Now we know Ohm's law, right? Which is V voltage is equal to the current I times the resistance R. So this lets us figure out what's going on when we have resistive elements inside of our circuit, and we have currents and voltages. Right, so now we know about this. But you know, whenever you have a circuit, it's not just strictly going to be some type of source that is being fed into a singular resistor. Now, eventually we'll want to start modeling things where it's, what if it was just a singular resistor? But now we want to start thinking about if we have more complicated topologies or networks that construct a singular circuit. Like, for example, over here off to the side, I'll draw. So we could have a source into a resistor, which goes here, and there's another resistor, say, and then maybe we branch off and we have another resistor right there. So that's one, and then you could put a resistor here, right, and then you could even put another resistor here. And you can see quickly how, okay, well, I know Ohm's law, and maybe if I know the voltage across here, I can find a resistance, or find current and voltage, but it quickly gets more and more complicated. And so we want to be able to take circuits that look like the circuit that I drew in white right here, and from its structure, from its geometry, figure out properties of that circuit, leading into actually analyzing it. So there are two fundamental things that we care about when we're looking at circuits, when it comes to circuit analysis. Okay, let's actually use blue. So 1 are loops. 2, we care about junctions. And let me draw a little thing. So we got loops and we have junctions. And I'm just drawing arrows because there could be things going into or out of those junctions. Junctions also could be synonymous with nodes. And then loops we'll see is synonymous with meshes. But whenever we care about a circuit, we have loops and we have junctions. And then how we're going to connect those to electrical properties. So loops really is connected to the conservation of energy. The law of conservation of energy. Which essentially all it's saying is that if you have a closed system, as in you can account for everything that's going on in this system, all of the energy is accounted for and you can't create or destroy it strictly within that system. If you had energy leaving or entering, then there's an external thing going on taking that energy or whatever. And then also junctions, connecting junctions, that would be the conservation of charge. Electrons, which have a fundamental negative charge to them, you can't necessarily create or destroy those charges. And we can go into that in a second. Conservation of charge. Okay. So, right, in this universe, energy cannot be created or destroyed. And also, electric charges cannot be created or destroyed. And so, from this, we can actually get some useful information when it comes to analyzing circuits. And so first we'll hit the loop conservation of energy connection. So let's start that with a different color. And this is going to end up leading us into what is called Kirchhoff's voltage law. So voltage in our circuit is fundamentally one of our sources of energy. And like I had said in the previous video, voltage is defined to be the derivative or the differential of work over the differential of charge. As in, if I have charges like positives and negatives and stuff, given all of these charges, how much energy can I impart? Or can I add? Like, how much energy do we have per charge? And that's really voltage or potential difference. And so this dW right here, this has to do with energy, which is in units of joules. This is our energy, right? And if it can't be created or destroyed, if we're looking within our circuit, right? If we're looking within closed systems in our circuit, so let me draw an example of a circuit again. Resistor, resistor. So if energy can't be created or destroyed, and actually let me label some things. So we'll have voltage VI for V in, we'll have VR1 for resistor 1. Let me label these guys, resistor 1 and resistor 2. So we have voltage across resistor 1, also voltage across resistor 2, right? So if this is this closed system and we can't create or destroy energy, then the net amount of energy in our system has to be zero, right? Because if the net is somehow not zero, that means that there is energy added or energy lost, right? And this can't happen because of conservation of energy. So what is the net saying? The net is just the sum of all energies. Net energy in this case. Net can be for anything. But so if we add all of these energies, and what we can do is go around this loop and add up all of the voltages, because the voltages are just talking about the energy for our specific charges in our circuit, right? So let's actually add up. I can't ever decide on colors. Let's add up all of these things. So then this is positive and negative. And so we'll treat the loop, we'll treat the direction of the loop as a current. So if we remember the passive sign convention that I was talking about last video, and that was, let's go here, passive sign convention. If we had our resistor and there was a positive voltage from left to right, then you would actually notice that positive voltage if there was a current I flowing into that positive. If the current was going the other direction, then your voltage would be negative. So this picture is saying voltage is equal to positive IR, and then if it's negative, if you were going the other direction, let's use a different color. If current was actually going in this direction, let's say I prime, then voltage is equal to negative I prime times resistance. So that's a distinction here that also follows into when we're looking around the loop of a circuit. So if we are going in the direction of this arrow around clockwise, then we'd be entering the negative side of this voltage, which would mean when we're writing the net, or we're writing the sum of these currents, or these voltages I mean, it would be negative VI. And then if we keep going clockwise, then we hit the positive voltage VR1, so we'll say plus VR1. And then as we keep going, we also enter then the positive terminal of VR2, so we'll say plus VR2. And then the sum of all of these has to equal 0 due to the conservation of energy, the law of conservation of energy, right? So now this gives us a way to account for all of the voltages or potential differences in our circuit. And this can apply if there are multiple loops in a circuit, you can apply those to all of those. And using Kirchhoff's voltage law is really important. And so the more formal definition for Kirchhoff's voltage law is that the, I'll say KVL, this is the sum of all of the voltages in your loop must equal 0. So this summation symbol, this capital sigma, is for a sum, right? So this is just telling us to add all of the voltages, and then I'm putting loop down here to signify we'll iterate through every voltage in the loop and add them together. So this is one of the two extremely fundamental rules that will help us analyze any circuit that we want. Kirchhoff's voltage law. Always remember, the sum of voltages throughout a loop must equal 0. This will be extremely useful in problems that we use. Okay. Now we want to talk about conservation of charge and how that lets us analyze any junctions in our circuit, right? So how did I say this? Kirchhoff's voltage law? Okay, so we'll say Kirchhoff's current law. This is now what we want to talk about. So imagine somehow that you've been tasked with looking at an intersection. And this is a traffic intersection. Since the beginning of time, your entire purpose has been to look at this intersection. But for some reason, there's like some fog covering the center right here, right? So you can't actually see what's going on inside of the intersection. All you can see, right, are cars entering and leaving this intersection, right? So as long as you've been looking at this since the beginning of time, you have been able to keep track of cars entering and leaving. And eventually would realize that there's like a conservation of cars. As in, if you see that pink car enter the junction, enter the intersection, you must see the pink car leave, but you couldn't somehow see two pink cars leave, right? If you're able to account for all of the cars that enter the intersection, you must be able to account for those leaving the intersection. And this partly assumes that all cars at some point leave and exit the intersection, right? That's a distinction. But you can't somehow get extra cars out of the intersection if they hadn't entered, right? So there's no generation of cars. No car is generated. But also, all of the cars have to leave, so there's no cars deleted from this system, right? And so this is the exact same thing that's happening inside of an electrical circuit at a junction. So say we have some conducting wire, it could be copper, and potentially here's a junction here. And so what you'll have, right, are your little charged electrons flowing through. And at this junction, or this node, is another very common and popular way of describing this. All of the charges, if they can't be created or destroyed by the law of conservation of charge, every charge that enters has to leave, right? So all charges Q are accounted for. You know, if you had someone do an audit of your electrons, they would eventually, it would take a very long time, but they would be able to count all of them, right? And by definition, current, right, is, I keep doing the wrong colors. Let's make this lighter blue. So if current is equal to the derivative of charge, dq dt, and don't get caught up on capital Q and little q, it's not too important. But if you are able to account for all of your charges, and as long as current is just the derivative of charge, you should then be able to account for all of your currents. So this is the fundamental building blocks for Kirchhoff's current law. So every current, let me label this with red. So every current I entering must be accounted for somewhere else in the junction where all of your current I's leaving. I'll make this I leaving. This could be I leaving 1, I leaving 2, I entering 1. Looks too much like an L. I entering 1. So all of your entering currents have to then equal the currents leaving, right? Because you can't somehow generate or remove charges directly at the junction. So this is Kirchhoff's current law, or KCL. So the sum of all of the currents entering or leaving your junction actually what I should say is all of the sum of the currents entering will be equal to the sum of all of the currents leaving. So this is our junction or node rule KCL, right? So now we have two really important rules here. We know now that because of the conservation of energy, all of the voltages in any loop in your circuit must add to zero. And also, we know if we're looking at a junction, all of the currents, maybe if I said junction up here, I meant to say loop. And then if we have all of our currents are entering our junctions, our nodes, those must add and equal to each other. So we can analyze circuits this way because what we can do is set up systems of equations now based on these rules, and we'll see that eventually. But just understanding that because of two fundamental laws of nature, conservation of energy and charge, we can deduce KVL and KCL, and we'll end up using those a lot in the future. Okay.